Welcome to the session 8 of Unit 2 in Digital Signal Processing. In this uh, session, let us try to understand the linear filtering techniques based on DFT, that is linear convolution using DFT. So before we go further, let us try to understand the difference between the linear convolution and circular convolution first, and then we'll go further. Okay, so if you see in the linear convolution, if you write here y of n is equal to x of n convolution with h of n. So let us consider this x of n is having L samples and h of n is having m samples. Then whatever the output sequence I get, it will be of L plus m minus 1 samples. Okay. So this is the scenario in the linear convolution. But if I will go for the circular convolution, then I can write the same thing. I can use the same signals. But if suppose this x of n has n samples and h of n has n samples, then ultimately this y of n is also having n samples. Okay. So if we compare these two things, then whatever the output I am getting using linear convolution and whatever the output I am getting using circular convolution, both are not same. If I want to make these both outputs same, then what should I do is I have to add m minus 1 zeros in x of n and L minus 1 zeros in h of n, so that the number of samples of x of n becomes capital N, number of samples of h of n becomes capital N, so that y of n will also have the samples equal to capital N. So that's what is the simple introduction for this. So let us go further now. So let us consider input sequence x of n with the samples capital L. So its samples are like 0, 1, 2, 3 up to L minus 1. Let's consider the impulse response of the filter and this impulse response of the filter. Let's consider its samples are M, capital M. So the sample numbers are from 0 to M minus 1. Then if you carry out the linear convolution, then what are the samples I'm getting for the output sequence? That would be capital N, and that is equal to L plus M minus 1. And just I have discussed that this, if I want the same output, then this x of n um, should be added with m minus 1 zeros, and h of n should be added with L minus 1 zeros. Okay, so that is what we'll see now. Is you are going to just adding 0 means we are adding the zeros. Okay, so let us see. Let's go further for that is the different steps for evaluating the linear filtering using DFT. So calculate the value of capital N. So you have to calculate this value capital N. Then next step is you have to add the zeros so that the length of x of n and h of n, length of x of n and h of n will become n. So if it is having the length, if it is having the length L, then you have to add m minus 1 zeros. If it is having the length m, then you have to add L minus 1 zeros, because n equal to L plus m minus 1. Okay, so you have to add this much zeros to x of n and h of n to make its length equal to capital N. So you can calculate the DFT of x of n, that is x of k. Then you can calculate the DFT of h of n, that is h of k. And then you can multiply x of k and h of k so that you will get y of k. Once I'll get the y of k, I can take its inverse DFT. I will get the y of n. So this is what is the procedure which we should follow for getting the output. Okay, for getting the output y of n. So let us move further now. Um, what is the hurdle in this, in the linear filtering, that whatever the real-time applications are there, all real-time applications, their input sequence is very long. Input data sequence is very long. So the title we have written as linear filtering of long data sequences. Okay. So what we have to do here is we have to split this long sequence. Yeah. So the same thing I have written here. So it is not possible to do the calculations for such long distances because of limited memory of digital computer. Okay. So if the computer is having limited memory and if I cannot process this long data sequences, then what I have to do is I have to split those data sequences into the small length sequences, or you can say it as I have to split the data sequence into the small blocks. So, and then we can say split the long data sequence into the small blocks. Then I have to find out, or I have to do the computation for each block separately. Okay, so for each block, I will do the computation separately, and then all these process blocks will be attached or fitted one after another to get the final output. So let us see how it is going to happen. Okay. So there are two methods for doing such computations. One is overlap save method, another is overlap add method. So let us see both these methods one by one. Let me clear the annotations. So first method is overlap save method. So in that we are going to do the filtering, or we are going to do the computation of each block separately. Okay, so let us go further now. So let us consider m is the length of the impulse response filter. So m is the length of impulse response filter, means h of n, its length is, let us consider the impulse response filter is indicated by h of n, and let us consider its length is capital M. Okay. So now consider any data sequence or input data sequence whose length is large, and this data sequence, now I have to, this input data sequence I have to divide into the number of blocks, and the length of each block, let us consider it is equal to capital N. Okay. So I am going to make the, I'm going to divide this input data sequence, I'm going to divide this input data sequence into the block of length N, capital N. Okay. Let's go further now. So in each block of length N, take m minus 1 samples of previous block. So in this you have to take m minus 1 samples from the previous block and L samples from the current block. Okay, so that this L and m minus 1, this m minus 1 and L, if you add, I will get capital N samples. Okay. So let's go further now. So you can see, and the very first block, in the very first block, you don't have any previous block, so you have to add m minus 1 zeros at the start of the first block. Okay, let us see how it is going to happen now. So I have the sequence, let's say x of n. So I have to divide it now. I have to divide the sequence into the capital N blocks, or sorry, capital N samples. Okay, this x of n I'm going to divide into the number of blocks, and each block is having the number of samples equal to n. Okay, and out of this n, I'm adding m minus 1 zeros here. M minus 1 zeros means m minus 1 samples will be zeros because it's the first block, and I will have the first L samples plus L. So I got here capital N samples in my first block, that is x1 of n. Okay, so let us go towards the next block. Now if I'll go towards the next block, what I'm going to do is I will take m minus 1 samples from the previous block. Means from this first block, that is x of n, I will take m minus 1 samples. Means from l minus 1, I will measure, I will calculate, I will compute m minus 1 samples, and that will m minus 1 samples I will consider here, and then I will consider next l minus 1 samples, new samples. So this is my L samples and this is my M minus 1 samples from the previous block. So I can write here like this. Ultimately I am getting here again n samples. So like this I will go further. Okay. Then I will go further and again I will uh, again I will let me take the pen. Again I will take M minus 1 samples from the previous block. Means from this block x2 of n, I will take M minus 1 samples and I will take here next L samples from x of n. Okay, so these are the L samples, new samples, and this is the M minus 1 samples from the previous block. So ultimately again it becomes capital. So again the number of samples of x3 of n becomes capital N. Okay. So in this way you have to split, you have to go on splitting the input sequence and you have to add the M minus 1 samples from the previous block. Okay. So let us go further now and so on. So in this way I have to do it till the end of my x of n. Okay. So let us go further. Let me delete annotations. So these are what we have seen in the previous slide. Okay. We have seen in the previous slide we have considered this we have considered this x1 of n, we have considered x2 of n, we have considered x3 of n, and so on. So let us go further now. And now what we have considered previously is we have considered h of n with m samples. Okay, so again you have to make the length of h of n also equal to capital N. So it is L plus m minus 1 should be there. So out of that, how many samples I have in h of n? H of n I have only m samples. So what remains is this L minus 1. So I have to add L minus 1 zeros to my h of n so that its length will also become capital N. Now once I got all the what we can say, once I got all the sequences of length capital N, once I got the impulse response with the capital N length, then I can easily find out the DFT for each block. Means for this block separately, for this block separately, for this block separately, and I will get here DFT of for the first block, DFT for the second block, DFT for the third block, and so on. Okay, up to last block. So let us go further now. So the endpoint DFT of each block is computed separately as x1 of k, x2 of k, x3 of k, and so on. The same thing just we have mentioned here. For x1 of k, x1 of n, I will get the DFT as x1 of k, x2 of n, I will get the DFT as x2 of k, x3 of n, I will get the DFT as x3 of k. Okay. So in this way, I can find out the DFT for individual block with the help of the h of n. So once I got this, so let us consider now there are many blocks are there. It means you have divided the input sequence in many blocks. So let us consider the mth block. Okay, let's consider DFT of mth block is xm of k. I have written here cap. So xm cap of a. Then the corresponding output is obtained as, and then the corresponding output would be like this. Yeah. So if it is, this is my input. Let me use another pen. If this is my input, so x1 of k, and if this is my impulse response, so if it is h of n, then its impulse response can be written as sorry, its DFT can be written as h of k. Okay, so this is the DFT of nth block, and this is the DFT of my impulse response. If I multiply it, I will get the corresponding DFT of nth block. Okay, so like this, I have to carry out the DFT of each block separately. So yeah, then what I have to do once I got this y1 of k, then I have to take its IDFT. Okay, so the corresponding time domain sequence is obtained by taking what IDFT of y cap m of k. So you have to take its IDFT. So I will take its IDFT. So by taking IDFT of y cap m of n, m of k, I will get y m of n. So I will get here y m of n is nothing but what nth block of x of n. So I will get here nth block of x of n. Like this, I will get just like this nth, I will get the zeroth block, I will get first block, I will get second block, I will get and so on. Because I will consider, I will get all the blocks of x of n here. Okay. Once I got all the blocks of x of n, then I have to add it. Okay, so similarly, time domain sequence of corresponding DFT of each block is obtained. The same thing I have just explained it. So once I got the mth block of x of n, then I have to go further. Now I have to see that I should not lose any information of original signal. Okay. So for that purpose, what I'm to do is now because of the circular shift of DFT, where we're using the DFT, where it's the prudent factor. So because of the overlapping of input data, there is aliasing in the initial M-1 samples in the corresponding output. So to understand this, we'll just go in the previous slide. Sorry. Just give me 1 second. Yeah. So what we have here is, yeah, you can observe here that you have these are the repeated samples. Okay, these samples are repeated because these samples I have taken it from the previous block. Again, these samples I have taken it from the previous block. So these samples and these samples will get overlap. These samples and these samples will get overlap. So there occurs a overlapping of the samples, and that I want to remove. Okay. So let us go further now. Clear all the rotations. So that's why to so the initial, so there occurs a balancing in the initial M-1 samples because there is a overlapping. If there is overlapping, there will occur a aliasing. Okay. So to avoid this, what I will do is I have to discard the first M-1 samples. Discard the first M-1 samples from the y1 of n. Means after computing the time domain sequences, the first M-1 samples are discarded from each block. So then after removing this M-1 samples, initial M-1 samples from each block, we can fit all the blocks one after the another to obtain the final output. Okay, to obtain the final output, what I have to do is I have to fit each block one after the another. But before that, you have to discard the first m-1 samples from each block. Okay, so this is what is the O11 save method. Let us go towards the uh, next method, that is O11 add method. So in this O11 add method, uh, we are going to consider the same thing. We are going to keep the size of each input block as capital N, and um, this capital N will manage, because uh, each input data block is formed by taking L samples, just by taking L samples from the previous input sequence and adding m minus 0 at the end of each input sequence. Okay, so let us see it in detail. So what I'm going to do here is, if suppose I have input sequence x of n, and out of this x of n, I'm going to consider the first L samples. First L samples means from, let's say, 0 to L minus 1 in x1 of n. Okay, the same thing is happening here. I'm going to consider x of 0, x of 1, x of 2 up to x of L minus 1 samples in the first block, and then I have to add m minus 1 zeros. So ultimately, these L samples and m minus 1 zeros, it will give me total number of samples as capital N. Okay. So similarly, if I go to the next block, in the next block also I have to consider next L samples. Okay, means in the next block also I have to consider L samples, but now I have to consider next L samples. So it is L minus 1. So I have to start with L and I have to end with twice L minus 1. So this should be my own x2 of. So this is my next L minus 1 samples and m minus 1 zeros. So sample number of samples are L and zeros are m minus 1. So ultimately its number of samples will become capital N, and so on. So like this, you have to, in x3 of n also, you will consider the next L sample, that is twice L to thrice L minus 1. So here I will get L number of next L samples. I will consider m minus 1 0. So ultimately it is n samples. Okay, and so on. So like this, I will go further. And once I go further, then what I know again is h of n. So h of n is having m samples. So I have to add L minus 1 zeros so that its length will become n. Then again, you have to carry out the DFT for x of n and h of n, so that I will get uh, x of k here. If I do, if I carry out the DFT between x2 of n and h of n, then I will get x2 of k. If I carry out the uh, if I consider x3 of n and h of n to find out the DFT, then I will get x3 of k. So like this, I will get the DFT x1 of k, x2 of k, x3 of k, x3 of k, and so on. Okay, so I can get the DFT of individual blocks like this. First block I will get DFT as x1 of k. Second block I will get DFT as x2 of k. Third block I will get DFT as x3 of k, and so on. Let us go further now. Let me delete all the annotations. So yeah, the same thing I just explained, that each block DFT you can find out x1 of k, x2 of k, and so on. So let us consider again the m block DFT as x1 of x cap m of k. Then the corresponding output is obtained as h of k into x cap m of k. That would be equal to y cap m of k. So it is the mth DFT of mth block. Okay. So like this, I can find out the uh, DFT of each block. Okay, and then once I got this ym of k, then I can take its IDFT and I can get ym of n. Ym of n is nothing but the mth block of uh, output sequence. Okay, so like this, we can Yeah. So similarly, time domain sequence corresponding to the DFT of each block is obtained just like this y m of n. I can get y1 of n, y2 of n, y3 of n, and so on. I will get the all blocks. Okay. Once I got all blocks, then the sequences would be like this: y1 of n equal to like this, y2 of n would be equal to like this, because uh, all these blocks will have capital N samples. Capital N samples. Okay, but out of that capital N samples, there are last n minus one zeros. Okay, so this one, this another, and just will go further. So like this, I will get last m minus one samples. Probably they are all are zeros. So in this method, each input sequence is padded with uh, m minus one zeros at the end that we have seen. So the last m of m minus one samples of each output block must be overlapped and added to the first m minus one samples of the succeeding block. Okay, so what are the last m minus one samples are there of the previous block? Means this you can say, and this should be added with the, let us say, first m minus block somewhere here. So to add this samples. Okay, so last m minus one samples of, let's say, first block should be added to first m minus one samples of second block. Like this, last m minus one samples of second block should be added to, let's say here, third sequence. So this should be added to the first m minus uh, one samples of, let's say, white shopping. Like this, you have to do the same thing I have just written here, that the last m minus one samples of each output block must be overlapped and added to the first m minus one samples of the succeeding block, means next block. So, and that's why uh, as we are adding this, so this last m minus one samples of the previous block to the first m minus one samples of the next block, we are calling this method as overlap and add method. Okay, so that's it for the today's session, and in next session we will try to understand decimation in time fast Fourier transform. Thank you.